from the University of West Virginia. The first paper, entitled Synthesis and Catalytic Properties of Molybdenum Sulfide Prepared by Vapor Phase Thermolysis and Molybdenum Hexacarbonyl and H2S, is co-authored by Michael Close, Jeffrey Peterson, Jinyu Liu, Youngho Lee, and Edwin Kugler, and it will be presented by Michael Close.
First of all, I wanted to say that I had my introduction to this type of research back at Weber State University in Ogden. They had a project, the organic chemists had a project where they were trying to extract oil out of the Great Salt Lake. The problem was it contained 13% sulfur. And so their objective was to get rid of all the sulfur so they could utilize the material. That was my first exposure to the problems of sulfur. On a research level. Coming here to West Virginia, I came here because of an intriguing project. DOE had funded a project where we were going to investigate the economic feasibility of converting coal-derived syngas to alcohols. Now earlier, Dave Minahan mentioned that the molybdenum gave pretty traditional distributions of alcohols and had been looked at before. One of the qualifications that we have in this project is that we have to make catalysts that are sulfur resilient. So before I threw up the molybdenum, I thought I'd better explain why we're looking at molybdenum, because it's not just an old hat catalyst. I think there are a lot of possibilities that that particular material and other metal sulfides can yield in terms of catalytic activity. So today I'd like to talk about the specifically about the synthesis and catalytic properties. We're involved in a collaboration between chemistry and chemical engineering at WVU and Union Carbide. You could call me the chemistry contingent. I'm making some of the materials that we're looking at that are being evaluated in the chemical engineering department. Today I'll be talking specifically about the synthesis and also about the properties of these materials. First of all, I want to give you an overview of what we're trying to do, the overall perspective as to the directions we're trying to take. Then I would like to show you that by using a vapor phase reaction and specifically controlling temperature, pressure, and the rate, the gas flow rate, you can affect change in surface area, composition, and crystallographic phase of these materials. And then next, I want to show you what we've been able to come up with in terms of the catalytic properties of these materials. Specifically looking at the alkali modifications of the materials, variations of the molybdenum reaction conditions, and the space velocity in the reactor studies. And I'll summarize that. Conclusion. I came in here with the idea that we're going to make materials, make catalysts, hopefully. That would be good alcohol catalysts. And so in developing projects, I looked at 4 different materials, or types of materials that I wanted to target. First of all, starting with the supported molybdenum sulfides, been able to make materials by using the potassium thiomolybdate and also the potassium MO3S13 compounds, dissolving them in the solvents and then supporting those on appropriate supports. Third area, in the supported molybdenum sulfides, using organometallic precursors, actually heterobimetallic compounds containing iron and molybdenum, cobalt and molybdenum, and nickel and molybdenum that could be decomposed. Something about my convention here. The solid dots are those that have been analyzed for their catalytic activities. The rings are those that have not been analyzed. In the bulk sulfides, specifically this is where we're going to be today, looking at making molybdenum disulfide with the vapor phase technique. We've also been looking at making Chevreul phase compounds and looking at their catalytic activities. and also making materials using a potassium sulfide polysulfide melt. And actually specifically making the potassium thiotungstate and other metal sulfides with this process. The third area is making supported molybdenum nitrides. Now, this process was initiated with some work I did through graduate school with a molybdenum azide compound that is soluble in pyridine dichloromethane that can be then supported on supports and alkalized to make a potassium or cesium doped molybdenum nitride, supported molybdenum nitrides. This is a fairly unconventional approach to the nitrides. Typically they're bulk materials, and these have been evaluated in a preliminary fashion. The last area, bulk carbonitrides, through the vapor phase reactor, I've also been able to make molybdenum and iron carbonitrides, and also the mixed metal molybdenum and iron carbonitrides. And I'd like to talk a little bit more about that in a few minutes. This is basically an overview of the materials that can be made with this vapor phase approach. Starting from molybdenum hexacarbonyl, reacting that with hydrogen sulfide, both in the vapor phase, could make molybdenum metal very easily. MoS2 can be made with the reduced molybdenum phase, and MoS2 can also be produced with this reaction. Going the other way, the molycarbonyl reacted with ammonia produces a variety of materials. Nitrides, this delta nitride phase, the hexagonal phase, the cubic form of molybdenum nitride, and also the hexagonal form of the molybdenum carbide. Going down to the iron compounds, the iron reacted with ammonia can produce a variety of carbonitrides. When the carbonyls are brought together in the vapor phase, prior to thermal decomposition, you can actually make mixed metal carbonitrides. And I haven't done this, but certainly mixed metal sulfides as well. We're going to be essentially right here today, just looking at one set of reactions, the molycarbonyl reacting with hydrogen sulfide, going to the molybdenum sulfides. This is a simplistic view of the gas phase reactor. I think it illustrates the important components of the reactor. First of all, we have helium or some inert gas or argon that is deoxygenated, dehydrated prior to running. Then we can use hydrogen sulfide or ammonia as the reactive gas. Both gases can be metered appropriately so that the stoichiometries can be controlled. The gases flow over the molybdenum carbonyl, which can be heated at a variety of temperatures, depending upon our needs. This actually controls the vapor pressure of the carbonyl. The carbonyl then is transported into a hot zone, ranging from 300 to 1100 degrees centigrade. The material passes through and is collected. Now let me make a note at this point. The materials that are made with this reactor are very, very fine particles. In fact, the particle size is around the nanometer range, but the materials are collected using standard filter paper. If you can imagine a vacuum cleaner, you have an idea of what we're using to collect these materials. Fortunately, nature is on our side. The materials agglomerate electrostatically, creating big enough particles to be caught in this filter paper. Therefore, we're able to isolate the materials very effectively. Critical variables here are the gas flow rates, the temperature that we heat the molybdenum carbonyl at, and the furnace temperature. And I want to look at each of those variables and how it affects the material. When I initially began these syntheses, this is the type of reactor that I use, essentially the same one you saw in the previous slide. Essentially, what we have here is we have a water jacket that allows you to maintain a constant temperature into the hot zone. The problem with this reactor is that we accumulated large amounts of metal. As the metal carbonyls decomposed, they accumulate on the inner surface of the reaction tube. So I modified the reaction tube to increase the yield, and as you can see, it increased it significantly. Basically, what we have here is a injector, a water-cooled injector, simply is what it is. The material goes here. You're able to maintain control of the temperature into the hot zone. The material shoots into the hot zone, is decomposed, and then is collected. There essentially is no collection of material at this point. And as you can see, the yields have essentially doubled by this modification. Now let's look at some data from these reactions. This is some data that I collected using reactor number 1. That's with the water jet at the top one that you saw in the previous slide. What you'll notice here, essentially the temperature, this is the furnace temperature, it's the gas flow rates. As the temperature increases, I would analyze the surface area of the corresponding materials. And what you'll notice here is that there is a maxima at 82 meters squared per gram. Now, this to me was a little bit surprising at first because I expected there to be a trend all the way through here. We submitted the materials to Union Carbide, and Golub Salita was able to do the XPS work for these materials. And what you'll notice more specifically, if you follow the molybdenum 3D energies down, you'll notice that the material prepared at 300 degrees centigrade has a binding energy of 227 EV. And as you go to the material to 500, that was prepared at 500 degrees, we have a binding energy of 229, which corresponds to that exactly of molybdenum disulfide. So what's happening here is at the lower temperatures, a lower valent molybdenum compound is being produced, and as is indicated by the binding energies of the material. And so really what we're seeing here is we're seeing a transition from some lower valent compound that has a relatively low sulfur amount to molybdenum disulfide. So that explains the anomaly. The decrease in surface area with temperature can be explained simply by annealing effects. And the higher temperatures will anneal the material and sinter the particle size. I wanted to do a more complete study of this, and so using the reactor number 2, that with the water-cooled injector, I looked at the temperature variation right there from 300 to 900 degrees, and looked at the corresponding surface area change. As you'll notice here, the surface area goes from 21 down to 6 up, and then down to 66.15. Now, the interesting point here is that, as you recall from the previous slide, the final material that we looked at, the surface area was quite low. And we don't see the annealing effects here that we did with the previous reactor. What we've done is shorten the heating zone by having that injector within the hot zone, and therefore the annealing effects have been reduced, giving us fairly high surface area materials at fairly high temperatures. Another thing you may want to take notice of is the sulfur concentration. The sulfur concentration at the lower temperatures is very low. For molybdenum disulfide, it's 40.06 is the sulfur amount. As you go then from 400 degrees to 500 degrees, it takes basically a fairly substantial leap to produce a material that is close to that of molybdenum disulfide. And so for these compounds, somewhere between 400 and 500 degrees, we're seeing a transition from a molybdenum carbonyl, probably an oxycarbonyl sulfide, to moly disulfide. Here we have the X-ray powder diffraction data for the materials I presented on the previous slide. Again, going from 300 degrees centigrade up to 900 degrees centigrade. What you notice quickly is the change in crystallinity as the temperature is increased. Essentially, the material at 300 degrees centigrade, very broad peaks indicative of a small particle size, and we know that it's actually indicative of a completely different material being prepared at 300 degrees. So the molybdenum disulfide is not prepared at 300 or 400 degrees centigrade. It doesn't come about until 500 degrees. And you can kind of see that in the X-ray diffraction pattern. So So we have a handle now on making molybdenum disulfide at a variety of surface areas. Simply by changing the temperature, we can make a variety of, or we can make molybdenum disulfide at surface areas ranging from 18 meters squared per gram to 120 meters squared per gram. The next thing I looked at was changing the vapor pressure of the carbonyl. Essentially, by changing the temperature at which it was heated, I could affect change in the vapor pressure. And going from a carbonyl temperature of 93 to 104, you'll see a corresponding surface area change from 95 down to 55.43. So what I'm essentially doing is increasing the flux of the reactor, increasing the concentration of the molybdenum carbonyl in the reaction, which then lowers, by increasing the concentration, we lower the surface area, which is consistent with any type of a co-precipitation reaction. As concentration is increased, typically you get a decrease in surface area. What you'll notice here too is the sulfur concentration decreases with increasing molybdenum temperature. The reason for that is, of course, you're increasing the amount of molybdenum carbonyl present and decreasing the relative ratio of H2S to molybdenum carbonyl, which is shown in the products of the reaction. Now, if the gas flow rate, that is the argon or the helium, is changed, we can look at here the effect of the argon. There we go. If you look at the argon flow rates here, going from 0 to 220 to 250, and the corresponding effect on the surface area starting at 120, going down to 63.98. So by increasing the flow rate, we actually increase the flux of the molybdenum carbonyl through the system, and necessarily lower the surface area. And again, the sulfur percentages drop as well as the flow rate is increased, or as the concentration of the molybdenum carbonyl is increased. Here's a diagram of the, again, an X-ray powder diffraction pattern for the materials you saw on the previous page. We're looking at the temperature of the molybdenum carbonyl temperature. Green is 93 degrees, 98, 104 degrees. In this case, what you see is you see an increase in crystallinity as you go to lower temperatures and higher surface areas, which may be exactly the opposite of what you would expect. Typically, one thinks of high surface areas, that is small particle size, as broadening the X-ray powder diffraction peaks. But in this case, what you're seeing is just the opposite effect. Why is that? I think what we're making here, and I've seen in the XPS, is that we're actually making something lower valent than molybdenum disulfide in this case. And so as you in this case, as you decrease the molybdenum temperature, you're actually increasing the molybdenum disulfide that's being produced. Or you're actually making more molybdenum disulfide as opposed to a lower valent compound. And that's how I would explain that. And I think that is borne out with the XPS data. Now, when I came to West Virginia, I was interested in looking at materials that were effective catalysts. One of the approaches that I decided to pursue was looking at lower oxidation state molybdenum sulfides. The first thing that comes to mind is making Chevreul phase compounds. Chevreul phase compounds are typically made